Here's a short Math156 script designed simply to show how to replicate exactly the results that are shown in section 3.6 of the textbook. You probably want to have the book open to that section while you're watching this video. So, this is a setup where you have a bunch of data about preferences of boys and girls respectively for 3 different types of candy, and I'm going to create the table of results from scratch. First, I'm going to make a matrix of the results. R-bind means bind 2 rows together. That's why it's R-bind. And the first row is the boys' preferences. The second row is the girls' preferences. I can enter the names of the rows as a vector. I can enter the names of the columns as a vector. And when I display this, it looks exactly like the table in figure 3.7 at the top of page 62 of the textbook. On the facing page, the textbook shows how to get the results of a chi-squared test in R, and we can do that directly by calling the chi-sq.test function, and that looks like exactly what's shown in the R note on page 63, or we can do it by hand. We define our usual chi-squared function where we have to calculate the expected number of preferences for boys and girls for the 3 types of candy, and this outer is a function that takes a little bit of getting used to. What it does is multiply something for the row by something for the column, and to be precise, what it does is for each row it takes the row sums based on the observations and then divides them up in proportion to the column sums. The effect of this is to get a matrix where the preferences of boys and girls are exactly the same, and then we sum over all 6 cells in that table, the usual observed minus expected squared divided by expected. And when you look at that, you get 3.290. That is exactly the result that comes out of the chi-squared test. So now you know exactly what R's built-in chi-squared test does. But actually we can do a bit better. We can simulate the actual survey, and here's how we do it. We make a data frame with 210 rows. Each row specifies candy preference and gender. So since overall there were 75 preferences for flavor 1 and so on, we make a vector with 75 repetitions of flavor 1, 47 for flavor 2, 88 for flavor 3. And then we look at how that was broken down between boys and girls. And opposite the 75 preferences for flavor 1, we put 42 boys entries and 33 girls entries, and so on. Out of these 2 vectors, we make a data frame, and you can see what it looks like. It's got a preference column and a gender column. And if we make a contingency table out of it, presto, we have recovered table 3.7 from the textbook. We can run a chi-squared test on it and get a p-value of 0.193. But you say there's another way of doing this sort of statistical test. I can do a permutation test using a chi-squared statistic and ask, how likely is it that this gender discrepancy could arise by chance? Well, if we just permute the gender column, we'll have the same number of boys, the same number of girls, the same number of preferences for each kind of candy. So what I will do is make a permuted gender column by just calling sample on candy $general. Remember, sample with only one argument just permutes the entries in the vector. And if you look at the head of this, it happened to start out girls, 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 boys, boys. That will change every time I do it, of course. It's useful looking at the result of just a single permutation. So if I make a contingency table from this, it's got the same row sums, it's got the same column sums, but it's got different numbers in it, and of course it has a different chi-squared value. So we do this over and over and over again. We'll do it 9,999 times. Fortunately, that happens very quickly on my nice computer. And I will make a histogram of the results. Well, you say, I've seen that before. That looks like a chi-squared histogram. Sure it does. And then I will draw a red line at the observed value, and I'll notice that there are a significant number of cases where with a random permutation of boys and girls, I got a chi-squared value that was more extreme. On the basis of that, I say this could perfectly well have arisen by chance, and if I look at the fraction of times I got a larger result. It was 0.199 times. That's remarkably close to the 0.193 for the built-in chi-squared test. Why are the results so close? That if you look at the histogram of the results and compare it with the density function for chi-squared with 2 degrees of freedom, you see an almost perfect matchup. Why 2 degrees of freedom? Well, you can say on the one hand, the formula says you take the number of columns minus 1, which is 2, multiply by the number of rows, which is 2, and subtract 1 from that. 2 times 1 is 2. But a nicer way of thinking of this is if you give me any 2 of the 6 entries in this table, knowing the column sums and the row sums, I can reconstruct the other 4 entries in the table. So there are really only 2 independent new pieces of information in this table. Okay, that finishes up this short topic.